So this is the end of that positive connector cable that connects the gun to the machine, and you can see like there's obvious signs of heat and corrosion in there, and I suspect wrapping a little piece of copper around the end of your wire is a great idea to help make better contact and you know, a few other things, but no copper wrapping is certainly a lot better than this kind of connection. And if you look at the ends of this, you can see little chunks like that and that, and I'd be willing to bet those are where arcing's occurring inside. So I guess at this point, I'm not terribly surprised that my first shot at welding with this was crap, and I think at this point I wouldn't blame the machine. So you can see here, I've cut the cable back twice in this case. The first time I cut it back, you can see the green right by my thumb. And the second time I cut it back, you can see that it's all nice and bright and clean. And that's how far you have to cut it back. And in the case of your ground wire especially, you could find that it's got green all down the length of it and it's corroded all inside. And then that means it's time for new ground wire. You know, I mean, if you're doing it, I mean, of course, I wouldn't actually replace it. I'd just peel it back and do the best I could. But man, in MIG welding, your ground wire is absolutely 100% essential that it be as good as possible. You know, this is the positive side, but it's all part of the same chain. And for reasons I don't fully understand, TIG is very tolerant of like a crappy ground, but MIG, it's not going to work at all. So this is the after with everything cleaned up, and the white goop is this anti-oxidation stuff I use called Ultra Tef gel. I actually got it for putting bolts in my vintage Land Rover because of the aluminum to steel reaction. This is what everybody loves, so it's anti-corrosive gel. I think it's a good idea. So anyways, you know, silicone grease would be fine. I just use that because I had it. And then I'm going to wrap this whole thing in electrical tape because obviously normally there's those big rubber connectors that sort of insulate this, but right now they're just hanging in the breeze, and you know, better safe than sorry. Okay, so here's my test setup currently. I've got my oscilloscope here, and it is connected in the back up there to where the voltage meter is on the front. Right now I have it in one of the configurations on my list. I have a list of configurations which should be linked down below. We're actually starting with the 60 microfarad bus bar 200 volt tap. So configuration 6 is what we're starting with. I'm going to work my way through all 11 of these configurations. I have the oscilloscope set now. And I'm going to be showing you the waveform both while I'm welding and while I'm not welding. The originator of this design says that, you know, whatever happens while you're not welding is unimportant because you don't have the flow of electrons to do the main bit of how this converter is supposed to work. We will see how that works. I know I can get a good clean waveform though of just that anyhow. I've got my settings set. My test piece is going to be the 16 gauge plate because it's clean and I don't have to do anything to it. It's fine. And I'll do like an inch bead of weld by each one of them. What I will be doing is adjusting each time. No matter what I do, I will crank the adjustment so that I end up with about 19 volts while I'm welding. I'm not going to change anything due to amperage. I'm not going to change the wire feed. I'm just going to be changing it so that it's outputting the same voltage for each configuration because, I mean, you're using different multipliers to get your voltage output, and some of them are going to be closer than others. And I'd rather be able to, you know, it seems like most of an apples to apples situation. As I talked about earlier, I have cleaned all the connections up on the front of the welder so that now I have a good connection, which made a world of difference. I won't be changing my argon settings. My wire feed settings will be the same. The only thing I'm changing is the wiring configuration and the amount of capacitors. I will be using for the 130 and 180, I will be using these CBB60 capacitors. I suspect that we'll find out that they actually do what they say on the tin. now that I've played with this a little bit and seen some of the outputs. But I think if I was doing this conversion at home, I would absolutely spend the money and get the oil-filled Dayton caps. I mean, these I got right from Grainger, and they were like $20 each. I'll put all the part numbers in a list once I figure out exactly the optimal way to configure this machine, which this is the CP-300 with the 200 volt taps, and obviously the CP-200 that doesn't have those extra set of taps, that only has 4 taps, not 6, will have a different optimal configuration. So anyways, without further ado, what you'll see next is I'll show you the waveform, both welding and not welding, and then at the end I will have a list here. I'll just take a Sharpie and write above each weld that I do what the configuration was, and I'll be doing test welds each time over here just to make sure that you know, everybody actually has a chance at this. So without further ado, let's get going. All right, this is configuration 1. This is the 200 volt taps wired, and this is open circuit. There's no capacitors, no capacitor driven third leg, if you will. So no capacitors versus capacitors on open circuit doesn't seem to make any difference at all, which I guess is to be expected. All right, and just a sniff under 200 inches per minute. All right, that's test number 1. Now we still have to do 8, 9, and 10, geez. Okay, this is test number 2. This is with the 260 microfarad oil-filled capacitors. And this is an open circuit picture. Again, looks about the same. And we'll do a welding one. So far, it seems like only one of these really looked interesting to me. So I'll do an inch on my test piece, and we'll be able to come back and look at all of them when I'm done. So this is test number 3 with the 130 microfarad Chinese capacitors. And the only reason I'm really doing this and the 60 test is just to see if the capacitors, if the cheap Chinese capacitors are actually doing them. These are like the polymer film type. They feel really weird. So here's the signal, shorted. Looks pretty similar to what we've been seeing a lot of the time. Oh. Okay. It didn't feel too much different from anything else. So far, number 7 is absolutely the winner. Even though it's got a lot more voltage than I ideally like, I think. All right, this is configuration number 4. This is the original wiring, except with 180, or the original wiring for the CP-300 with 180 microfarads on it. So this is with no wire feed. It's interesting, that's a much shorter wave there. Oh, I gotta also adjust the voltage way up. All right, this is the welding with the 200 inches per minute-ish and about 19 volts while it's welding. Interesting. I don't know what that means. Feels good though. This is configuration 5. This is with no capacitors whatsoever. Currently open, no welding. That looks about the same to me. Let's see what happens when we weld. This is test number 6, 200 volt taps with the bus bar and 60 microfarads of capacitance. This is non-welding. This is with the feed turned off. So that's what it looks like. So you've got this ends up, if you do the calculations, at each peak is 120 hertz because you've got 60 hertz that's rectified. Even though you have 2 legs out of 180 degrees out of phase, that doesn't matter because you're gonna flip the downs to the ups and the ups will already be up. I'll give you a better description somewhere else. Yeah, so I suspect if the capacitors are doing anything, they're why it's a little bit flat on the top, but I don't know that for sure. I'm going to turn the wire feed to 200 inches per minute, and we'll see where that gets us. This is test number 7. First, no welding at all. And that's interesting. This is the one with 180 microfarads of capacitance. That is a different signal than what we've seen before. And I think what we're seeing is that generated leg, I noticed, got pulled down, but you can see right there that it's actually trying to do something, which, all right, I'm starting to believe, but I'm thinking that the amount of capacitance we need is going to be in like 300 to 500 microfarad range to really make it happen. I think that welding waveform was a lot smoother as well. I'm gonna go actually do a weld with it and we'll see when we get completely done. So this is test configuration number 8 with the 480 or the 460 volt taps selected like in the original PDF, but this is with no capacitors. This is open circuit. And man, that always looks just about the same, doesn't it? And this is welding, which looks just about the same. So we're gonna add some capacitors in a few more steps, and then I will tell you the way I think is the best way to wire this puppy up. This is configuration number 9. This is the 460 volt taps with 60 microfarad oil-filled caps involved. This is open circuit. Looks a little different than normal. And this is welding. Okay. This is wiring configuration number 10. This is 180 with the 460 volt taps with the bus bar in there. Again, with 180, you start to get that little extra kick in there. That looked awful smooth to me. Okay, that's all 10 configurations. I decided not to do the 11th configuration because things seem pretty consistent. That would have just been just the 130 microfarads with the same configuration as number 10. I have my whole line of attempts. Now, I'm not a particularly good welder, but you can absolutely see a difference out of 2 of them. So we're gonna look down here, and that's 1, 2, 3, 4, 5, 6, 7 looks really good. 8, 9, and 10. Now I will say you can see that 7 and 10 are burning through a little bit. And what it was is even at the lower end of the scale, I could only get it down to 20 volts. But both of those are using the bus bar and 180 microfarads. And the output didn't really matter if you were using the 200 volt taps or the 460 volt tap configuration. But that's what the weld should look like. Those also had a much smoother output while welding, and a much different output even on an open circuit. I'm tempted to try with the Y configuration a lot more capacitors, but the Y with 180 degrees is number 4. It just doesn't look any different from number 3 or even 5 or 6. And some of this is just due to like me not being a terribly good welder. You know, 9 looked okay, but you notice even on the Delta configuration, you've got 5, 6, and 7, 0, 60, and 180. 0 and 60 look the same, and you get to 180, and you get that magic number. On the 460 volt taps, 0, 60 looks better, and then 180 microfarads looks the best. I'm looking for like a smooth, consistent weld that's nice and hot. This also definitely had more than 100% penetration, but they all kind of did. So, I mean, 16 gauge isn't the perfect material to be welding with this size welder anyways. It's just a spare piece of material I had that I didn't mind screwing up some of. So, I guess the takeaway is that I would go, looking at this and looking at my results, I would go with the 460 taps as in the original PDF with the bus bar and at least 180 microfarads. It doesn't seem to matter if they're these cheap capacitors or if they're the good capacitors. I think I might buy more of those for long-term usage. I'd like this to work for a long time. I'm also going to change this jumper wire and this jumper wire out for 8-gauge wire because that was the original. I'm not concerned with putting 8-gauge wire on the capacitors because they can, they only have so much capacity. They can only pass so much amperage. So bigger wires on them, it isn't really buying you anything. I could even go smaller because there's just not that many amps passing through them. There can't be. The bus bar there is just a piece of 1/2-inch copper pipe. I cut it using a scroll saw, and that worked out pretty well. So I guess that's it. That's 10 different configurations of the same welder. Trying to run it on single phase, and it looks like 180 microfarads per leg is the magic number, and it doesn't really matter if you use the 200 volt taps or the 480 volt taps. I want to look at this a little more and think if I can try just a couple more things with it to see what the difference is. I'd like to get it so that the display reads similar to the output, and I'd also like to get a little less output out of it because I would like to be able to weld 16 gauge with it, and it's clear the thing is just outputting way too many amps and way too many volts. So right now I'm set to just about 14 volts. I'm getting like 20, 21. So it's not terrible, and certainly a little bit more is probably better than a little bit less. But I'll let you guys know if I come up with anything different. But I suspect this is going to be the final configuration of the welder. Not this, of course, but tucked away, cleaned up, zip tied. I'll put a picture of like the finished shiny product in the end of it all. But yeah. So this channel being called Theoretically Practical, the premise of this was that it is theoretically practical to buy a 3-phase welder and convert it to single phase for all your welding needs to save money. Now, this whole machine with all the wires and everything I needed to get it going was $500. The welding tank, I'm leasing it by the year, but the tank and the fill-up in the first year's lease was like $175. And then, a $30 roll of wire and, maybe $100 worth of various wiring components, some of which I needed, some of which I didn't need. So I guess you're looking at like $800, $900 at the end of the day to go from no welding capability to a really nice setup. The other thing to be having consideration is I ran these for my TIG welder, which draws more amperage. So these are pretty overkill on the wire size for this machine. But to run this, to get 60 feet of this size cable was a couple $100 as well. So don't forget about that. And then, of course, it can keep adding up because you'd want a nice cord on it. And that cord will work for this machine. But I need a 6-3 cord for my TIG welder. So that'll be another $100 or so. And then I bought this connector used on eBay because it matches the one that was on there. And I bought a couple of plugs, and together there was another $100. So, don't go into this thinking, oh, I got this welder for $500, or maybe you got a better deal than I did. You've only paid $200 for it. And, oh, you got this great deal and you'll be welding for a couple $100. Well, it's just not the case. The other thing is I have on order the set of proper rollers for this application, which is, again, another $50. So It really does add up, but I would say, in my experience, once you've spent the money, you've got the machine set up, you will use it if you're the kind of person that thought this was a great idea in the first place. I absolutely recommend it at the moment, and in a month or so, I'll probably do hey, I used this machine for a month. This is what was great about it. This is what sucked, and let you guys know how it's worked out. So right now, I got to clean up the wiring, upgrade these wires at least to the right size, to 8 gauge, because that's what the original manufacturer uses. Probably overkill. 10 gauge is probably fine. These aren't, after all my testing, aren't even up to room temperature practically. And put the wheels back on it and a few other things. But I should be rocking and rolling pretty soon with this, and that's pretty damn good.